All right, so looking at the wheel here. All right, this problem is in your textbook as well if you wanted to double check it. But we need, let's draw a picture here quick. So we have our wheel, okay, and then you have a central axis that does not turn, so maybe that's on an axle or something like that. But this is our wheel. The wheel spins. If you have a mass of 15 kilograms, so the mass of the wheel, 15 kilograms, diameter of 0.44 meters. So we don't want diameters, we want radius or radii, so that's 0.22 meters if we cut this in half. Okay, and starts at rest. So we need, so angular, since it's a rotational system, our angular velocity from rest is 0, and that's radians. Let's get rid of that. Let's fix that a little bit. Okay, so 0 radians per second. Okay, and we want to increase the wheel's rotation to 8 revolutions per second. So our final angular velocity is going to be 8 revolutions per second. That's revs per second. And we don't ever want to really work with revolutions per second when we're dealing with angular velocity, because that will not agree very much with our Newton's law there. So we can fix that in a minute. And our time is 15 seconds. Okay, so A, what torque must be applied to the wheel? And then B, how much force should you exert on the strap? Okay, so let's see what we can do here. So let's write out Newton's second law of rotational motion that we just talked about. So net torque on top there, and moment of inertia on bottom there. So angular acceleration is equal to the net torque divided by the moment of inertia. Okay, and let's write out those equations. So torque is going to be force times a radius. Moment of inertia here, since we have, it's a wheel, it's a cylinder. Okay, so the picture in the textbook shows a solid cylinder. That is 1/2 mr squared. And then our angular acceleration, might need to move, let's get rid of this guy for now. So our angular acceleration, if you remember that one, that is equal to final minus initial angular velocity over time. So what can we solve over here? Well, we have a final, initial, and time right there. That can get us an angular acceleration. And we have a mass and a radius, which can get us our moment of inertia. And we don't have a force, which that's what we're looking for right there. So let's find this and plug it into Newton's second law of rotational motion, and that will help us find that force we're looking for. Okay, so let's do moment of inertia first. So 1/2, mass is 15 kilograms, and our radius is 0.22 meters squared. So put that in your calculator. So 0.5 times 15 times 0.22 squared, you end up with 0.363. So 0.363, and again the label is kilograms times meters squared. And so that's one thing we're going to use. And let's get our angular acceleration here. So we're going to do final, and again we had to change that, so let's do that here quick. So if we have 8 revolutions per second, and we want to convert, okay, so that's 8 revs in 1 second. We're going to do a little track here. So what's our conversion here for revolutions? We want to go from revolutions to radians. Well, 1 revolution is 2 pi radians. Okay, and that will get us to radians per second. So the revolutions will cancel out. So we just take 8 times 2 pi. That's usually the quick way to go from revolutions to radian. So let's write that. So final angular velocity is going to be 8 times 2 pi which is 50.27. And that is in radians per second. That's what we want. Okay, now let's use our angular velocity. So we're going to do final, which is at 50.27, minus initial, which is 0, so we don't really need to write that, divided by time, 15 seconds, and that gives us an angular acceleration of 3.35. So that equals 3.35, and that's radians per second squared. Okay, so that's the other piece we're looking for. So let's use those in our formula now. So moment of inertia, angular acceleration right there. So we have 3.35 radians per second squared is equal to my torque, I don't know. Okay, I'm making a curly torque for tau divided by moment of inertia, 0.363 kilograms times meters squared. And then how do we get that at the bottom? Just multiply by it. 0.363. 0.363. So that's gone, that's gone. We gotta multiply those two here. So 3.35 times 0.363. And we get a torque of 1.216, so 1.22, and that'll be Newton meters. And now we're trying to get the force out of this, okay? So torque, again, torque equals force times radius. So we can plug that in for torque, 1.22 Newton meters. We don't know the force, and we know the radius. Let's check it. It was 0.22 meters. The radius 0.22 meters. Divide by that. And we get 5.53. So my force is equal to 5.53, and that would be in newtons. So that's how much force we would need to get it to go from 0 to 8 revolutions per second. Okay, so if we apply the torque by wrapping a strap around the outside of the wheel, how much force would we have to exert on the strap? So I kind of did A and B at the same time without kind of realizing it. It says what torque must be applied to the wheel. That's our 1.22 newtons, so that's the answer for A. Oops. And then this would be our answer for B. So we kind of did both of those at once. Okay, so hopefully that helps show you how Newton's second law of rotational motion works. We have another problem on the next slide, so let's check that out quick. Okay, so I did this previously. Let's get rid of all this. Okay, so the wheel in example problem 4 is accelerated from rest to 8 revolutions per second in 5 seconds. So the difference here is our time is equal to 5 seconds. Okay, and we're going from 0 to 8 revs per second. So let's backtrack here, see if we can use some of the stuff on the last slide. So we are not changing our radius or anything. So we got 0.363 kilograms times meter squared for a moment of inertia. Okay. And then our angular acceleration, that's going to change because we're not doing it in 15 seconds anymore. We're doing it in 5 seconds. Okay. But we're not changing the 0 and 8 revs per second. So that's going to be 50.27 again. So it'll be 50.27 divided by 5 rather than 15. So 50.27 divided by 5, that's going to change our angular acceleration. So that makes it 10.05. And that's radians per second. Okay, so now we should have everything. We might need that radius again, 0.22 meters. if we don't remember it, and our mass was 15 kilograms. I don't know if we need that right now. So we have this. So second law, and that is over moment of inertia. So acceleration is equal to net torque over moment of inertia, and we will be looking for the force again. So we can find our torque, use our radius, we'll get our force. So we got 10.05 radians per second squared. I forgot my little squared down there. That's equal to net torque over moment of inertia, which is 0.363 kilogram times meter squared. So again, just multiply that out, and we will get a torque of 3.65 Newton meters. Okay, so now we'll use that in our torque equation. So 3.65 Newton meters is equal to force times radius. So force we don't know times the radius. So we'll just divide by 0.22 meters. And we will get a force equal to 16.59 newtons. Okay, so we're going to have to apply a 16.59 Newton force in order to do that in 5 seconds. Okay, so if we think about this, our time here is 5 seconds. Before it was 15 seconds, and we had 5.5. So we're cutting our time down by 3, right? So we're doing 1/3 the time. So really, if we're cutting our time down by 3, then our force should have to be 3 times as much. Okay, so if we look here, we had 5.53, which that makes sense that we had around 16.59. So that'd be about 3 times as much force to get it to go that fast in 1/3 of the time. Okay, so that's how we use Newton's second law of rotational motion. Okay, so that again is our acceleration is equal to the net torque divided by moment of inertia. So this is a little equation, is quite useful. It does have a lot of pieces to it because that blows up into a bigger equation, that does, and that does as well. So this equation with 3 variables actually has 3 different equations in it. So pretty useful. So hopefully that makes sense.